Okay, ladies and gentlemen, we are busy looking at the quantum mechanical description of three-dimensional rotation. And we said that there are two quantum numbers relevant to the system, both ML and L, where L goes from 0, 1, 2 to infinity, and ML is determined by L, and it runs from L minus 1 up into minus L. We also said that the number of ML values are determined by L, and there are two L plus 1 values of ML. So these are the two quantum numbers that are relevant. If we go back to the notes, I just wanted to mention something regarding directions and the representation of angular momentum. I just want to point out that when we talk about direction, we always view along the positive z direction. And that's how we define clockwise or counterclockwise. So if we have our z-axis in that direction, and that would be positive z, so negative z would be in the opposite direction. If you view along positive z, and the rotation is in that direction, it would be clockwise, and ML would be positive, and the opposite would be negative. Now you need to specify this, otherwise there are two possibilities for the direction. So if I were to illustrate it with a simple model, I just have a piece of filter paper and a pen, and let's say the tip of the pen is the positive z direction, or the positive z, this is negative z. So if I were to hold it like this figure, this arrow indicates the direction of rotation. So rotation happens in this direction. This would then be clockwise if I view it along positive z. So down the pen, this is clockwise, so that is positive ML, and in the other direction would be negative z. So basically what you need to know, you need to look down positive z, along positive z. Otherwise this is ambiguous. If you turn it around, you're going to have a different direction. So in this case, with ML smaller than 0, this will give you counter-clockwise rotation. So ML negative. Okay, we can also indicate the component of angular momentum along the z-axis, which is in this direction, using a vector of length ML along the z-axis. And we'll see why we can do this in a minute. Remember we said Jz is equal to ML h bar. But we know the values of ML, so these values are determined by L. So we expect this component of angular momentum along the z-axis to be quantized, because we've got a quantum number here. So the component of angular momentum about the z-axis, so this whole description is Jz, may only take 2L plus 1 values. Why? Because we have 2L plus 1 values of ML, of this. So we're seeing quantization in angular momentum. So let's represent the angular momentum with a vector. So guys, don't confuse J with Jz. J is the total angular momentum. Jz is the projection of that momentum on the z-axis. so the component along the z-axis. So let's represent angular momentum with a vector proportional to its magnitude. Remember, we said the magnitude of angular momentum is related to L plus 1 to the half h bar. So we just leave out the h bar, so we say the size is proportional to that, or the magnitude. Sorry, the length is proportional to that magnitude. And then we use the projection. In that case, we'll have a value of ml. Jz will have a value of ml. So if j is represented by a vector of that length, Jz will have a value of ml. So let's show this graphically, then this will make more sense. So let's consider the case where L is equal to 2. So ml is equal to 2, 1, 0, minus 1, and minus 2. And all of this is represented in this case. So for L equal to 2, J, which is the angular momentum, we represent with a vector proportional to L plus 1 to the power half. So J is the same for all of these. And this is our J vector. So the J vector is the same. That one, that one, that one, that one, and that one. However, the projection of J on the z-axis, now remember the z-axis is in that direction, must be equal to ml. So the projection must be 2 or 1 or 0 or minus 1 or 2. And how do we change that projection? Or how do we get these values of m? Well, because z is always in that direction and the angular momentum is always perpendicular to the plane of rotation, so J is always perpendicular to the plane of rotation, the only way that we can change this is by changing the rotational plane, the orientation of the rotational plane. So if the plane has this orientation, J is always perpendicular to that plane, the z-axis is always in this direction, then ml has a value of 2. So for this specific rotation, only by having this plane in this position can you get ml equal to 2. If we change the orientation of the plane, again J is perpendicular to the plane of the circle. The z-axis is again in that direction. So to make ml equal to 1, ml is the projection of J on the z-axis. That can only be achieved by having this plane orientation. For ml equal to 0, basically the projection is just a point. ml equal to minus 1, now we're moving into the negative z. So positive z is above the plane, negative z is below the plane. Again, this can only be achieved with this orientation of the ring. And then lastly, for ml minus 2. So what are we seeing here? We're seeing that the rotation is quantized. We can have rotation like that or like that, but we can't have something in between. That's not allowed. You can have that one and that one, but you can't have something in between, because that will give you an ml value that's not acceptable. Same for anything in between that or in between that. So the classical interpretation of this would mean that the plane of rotation of the particle can only have certain discrete orientation. And the quantum mechanical interpretation is that the rotation of a rotating body is quantized. It cannot take an arbitrary orientation relative to a specified axis, which in this case is our z-axis. It can only take certain orientations relative to the z-axis. Now this quantization of rotation was proved by Stern and Gerlach in 1921, or so they thought, but we come back to that experiment in a minute. So think about what this means in the macroscopic world. It means that if you kick a soccer ball, it can only rotate in a couple of ways. It cannot rotate in any way, which is of course is a very strange concept. Okay, so let's look at the experiment by Stern and Gerlach. So what they did is they used silver atoms that they shot through a magnetic field. So if you look at the electronic configuration of silver, you'll notice that there is one unpaired electron. So that unpaired electron makes a silver atom behave as a magnet because it has an unpaired electron. And let's assume the orientation of the angular momentum, so this J that we've said has to be quantized, can take any value. If it can take any value, the magnetic field will allow the atoms to be spread in any direction. So this is what we expect if there is no quantization of rotation, because there's no preference for a specific orientation of angular momentum of that electron. However, this is not what they saw. What they saw were two clear, distinct spots on this detector. So there was definitely some kind of quantization. Two different types of silver atoms. One went in that direction and the other went in that direction. So the interpretation of this was that in quantum mechanics the angular momentum was quantized. However, this is not the full story yet. We will come back to this. The section on quantum dots you can read. This is not for exam purposes, but it is quite interesting. Okay, so let's go back to the Stern and Gerlach experiment. Like we saw here, they observed two different spots or bands in the experiment. But this is a bit confusing. For a specific angular momentum L, you have 2L plus 1 orientation. Now we have two orientations, or two bands. So that means two values of ML. So what does L have to be to make the 2L plus 1 equal to 2? That is when L is equal to half. But remember, we said L is equal to 0, 1, 2 to infinity. L cannot be a half. So what they actually observed was not orbital angular momentum quantum number, or orbital angular momentum given by the quantum number L. What they observed was what we call intrinsic angular momentum, or spin, of this electron. So remember, if we have a look at the electron configuration of silver, they saw the spin of that unpaired electron. And there are two different possibilities, two orientations of spin. And that is why they saw the two bands in the experiment. So now we have to be careful because we're talking about two different things. Different boundary conditions apply to an electron spinning around its own axis than those that apply to a particle circulating around a central point. So we have different restrictions for what we call spin, angular momentum, quantum number. So make sure you understand the difference between the two. On the one hand side, we have the quantum number L, which is the orbital angular momentum quantum number. And a very simple and probably not correct way of visualizing this is to see this as the angular momentum the electron has because of moving around the nucleus. It orbits the nucleus, therefore we call it the orbital angular momentum quantum number. Now we've also just defined a new quantum number, which is the spin angular momentum quantum number, and we use the symbol S for that, lowercase s, and that is the spin of an electron around its own axis. So if that's our electron, it spins around its own axis. So these refer to two different types of angular momentum, the orbital angular momentum and the spin angular momentum. And for each of these, we have a different quantum number. So just to summarize that, we can now distinguish between the spin quantum number S and the corresponding spin magnetic quantum number ms, which is the projection of S on the z-axis. So these refer to spin around the electron axis. Then we have the orbital angular momentum quantum number L and the magnetic quantum number ml. These refer to an orbital motion. Now, many of the equations that were applicable to the orbital angular momentum are also applicable to the spin angular momentum. Remember, we had a similar equation for the magnitude of the orbital angular momentum, where we just had L's in this equation. The number of, remember we said ml takes 2l plus 1 different values, ms takes 2s plus 1 different values. ml goes from l minus 1 to minus l. ms is very similar, but just remember we call it spin, but it's not really a spinning motion. It's really an intrinsic property like mass and charge that the electron has. Now, for an electron, only one value of S is allowed. S equal to a half. So for an electron, S is always equal to a half. If you then use that to calculate the magnitude of the spin angular momentum, you get a value of 0.866 h bar using this equation. And this is again an intrinsic property of an electron, like its mass and its charge. So every electron has the same value for S. There are 2s plus 1, so two different orientations for electron spin, ms plus a half or ms minus a half. We call this alpha or beta spin or up or down spin. So if we go back to the Stern-Gerlach experiment, each of these silver atoms has that one unpaired electron. Some of them has a spin of plus half ms, some of them have a spin of minus half ms, and that is why we see the two bands in the experiment. So electrons have spin, but other elementary particles also have spins. Both protons and neutrons are spin half particles, and the spin angular momentum corresponds to that of the electron. The photon is a spin 1 particle, and you can use that to get its angular momentum. And then, depending on the spin, we can distinguish between a fermion and a boson. So all particles that form matter are fermions, so spin half particles, but particles responsible for forces are spin 0 or 1 particles with integer spin values. So you'll notice that there is a table in your notes that summarizes all of these quantum numbers and also summarizes the names of the quantum numbers and the symbols that we use. And that basically ends off the chapter 9 or 8, depending on the edition of Atkins that you have.